Hey everybody, Dave Lindbergh in Hong Kong with another episode of THD Podcast. Today we have a company from Israel joining us to tell us about their MEMS speaker technology. Interesting stuff, a growing category definitely in audio and micro speakers for sure. But without delay, let's not forget to mention Alti, our sponsor, and they've got the Alti Expo coming up June 11th to 13th in Orlando. So we encourage people to check it out if they're going to be stateside. Please attend. There's actually going to be a live audio product development alliance, which is a new association making some presentations on different aspects of audio product development. So we encourage people to check that out as well. But without delay, let's get to our discussion today. So Simon Weston joining us from Japan. Good afternoon, Simon.
Hey, Dave.
Hi, all right. Always enthusiastic. And Moti Margalit, CEO of Sonic Edge, and Ari Misrahi, COO. Thanks for joining us today, guys.
Hi, thanks for having us.
Thank you. It's a pleasure.
Okay, great.
Having with you.
So yeah, I always kind of fumble through, but it is a MEMS speaker technology, and this is kind of a really growing category. How about we jump into a presentation quickly to tell people what it's all about?
Okay, thanks, Dave. So while Sonic Edge is making a MEMS speaker, we're really doing a new kind of sound source. We're using MEMS technology to enable it, but it's important to understand that we're taking a fresh look at how speakers are made. Actually, not much has changed in the physics of speakers since they were invented. A moving membrane pushes air, generates sound pressure, and this is what we hear. Much of the aspects have changed, but still the physics are the same. And other MEMS speaker companies are trying to do this using MEMS technologies. We took a different approach. We took a first principles approach to the problem, and we asked ourselves, we want to make a really small speaker. What should we do? So looking at like the woofer is large, the tweeter is smaller, a really small speaker really is good at generating ultrasound. So that is our starting point. The speaker, the thickness of a hair is generating ultrasound. We put several hundred of these speakers on a 3x3 millimeter silicon chip, and that's the basis for the speaker. That's a very good ultrasound speaker. Problem is we are not bats. We can't enjoy that music. So we somehow need to take that ultrasound and transform it into sound. In the past, people have done what's called a parametric speaker. That means they used a lot of ultrasound, so powerful the air becomes nonlinear. You have self-modulation and sound generation. That is very directional, has many limitations, requires a lot of power, is not efficient, requires a large speaker. So at the end of the day, it's a good solution if you want a directional speaker, but not as a general speaker. Instead of doing that non-linear self-modulation, what we do is active modulation. That means above each one of our speakers, we have a small acoustic channel. I'll get to that in a slide or two. And that we can control the dimensions of that acoustic channel. By making it smaller, we attenuate the ultrasound. So the result is we can modulate the ultrasound and generate sound from ultrasound using a mechanical structure. So our speaker is really an ultrasound speaker and an acoustic modulator. One may ask, okay, sounds nice, but why does this make a smaller speaker? The answer is that as you look at the physics of this, and again, I'll get to that in 2 slides, what we have done is really create a small pump, the width of a hair, and working at several hundred kilohertz. That means that if we compare ourselves to a standard speaker, let's say pushing air at 1 kilohertz, we have 400 times more opportunity to push air. That enables us to make the speaker 10 times smaller, to make the displacement 10 times smaller, and still have room to spare for the SPL. In an earphone situation, this also means that as we go down in frequency, this advantage increases. And this is something that we measure all the time. A pump speaker, as you go down in frequency, has an increase in the attainable sound pressure level. You have more time to build up pressure at 100 hertz compared to 400 kilohertz. the advantage is 4,000 and not 400. And this is, again, something we measure. So our speaker is really an ultrasound pump, highly efficient, and pushing air at audio frequencies, creating sound through that. Because this is a silicon device, we can do to speakers what LEDs have done to lighting or electronics or transistors to electronics, a solid-state speaker, a scalable solution for the audio. So coming back to the technology, you can see our structure here, and the total thickness of this structure is less than 10 microns. We have the ultrasound speaker generating ultrasound. It's going through a middle membrane which has a perforation, so the ultrasound can go through this acoustic channel. When the top membrane is in the down position, we are attenuating the ultrasound. When the top membrane is in the up position, we're letting it go. So this is the modulation action. By moving the top membrane, we're modulating the ultrasound and generating sound from ultrasound. The pump action can also be understood if we look at both of them working at the same frequency. In this case, when the bottom membrane is pushing air, the top membrane provides an open valve and the air can flow forward. When the top membrane is in the down position, the back movement of the air is limited. So by changing the relative phase between the top and bottom membrane, we can control the flow of sound, the flow of air, and that is, of course, equivalent to generating flow and acoustic flow. So this structure is really the basis of our speaker, and we have 200 of these on a 3x3 millimeter device. We have three pads, one for the middle membrane, a top and bottom membrane. The actuation is electrostatic. And one of the key features of our device is that really we have a very low capacitance, much smaller than all the other MEM speakers on the market. And this enables us to achieve low power and very efficient operation. Our solution is a drop-in replacement for the speaker and the power amplifier. We provide an ASIC, which receives the digital audio signal and generates the required ultrasound and modulation signals for the speaker.
Okay.
Our customers appreciate the fact that the small speaker is really a big opportunity in terms of what they can do with speakers. This is a mock-up of an earphone. It is about half the size of a standard earphone. There are many unique characteristics to having a pump rather than a standard speaker. We're agnostic to the back cavity size. We can work with a much smaller back cavity than existing speakers. We're also agnostic into what's in front of the speaker. So we can work with thinner tubes or look in situations where actually the speaker is inserted into the ear canal. All these do not affect our ability to push air. We can work up to very high back pressures. Some customers say, okay, if you're freeing up space, let's put in sensors there for 3D audio or biometric sensors, and others want more a larger battery for longer playing time. And our product offering doesn't end with earphones. We have solutions for headphones, AR glasses, and then beyond that, the cell phone market and other audio markets. But just the earphone market, I don't need to tell you, is already a huge market, and that is where our initial focus is. And our business model is to sell these components as a fabless company. We work with external fabrication plants to provide better sounding earphones. In terms of the company, I come from a deep tech background, having founded several companies and led development of innovative products. Ari?
Yeah, so I'm more into the sales and marketing and business development. My experience is, I'm an electronic engineer with an MBA, and I'm leading the sales and operations in the company.
We have a Danish subsidiary. Most of our investors come from Denmark, from the audio industry, and the Danish subsidiary is responsible for the electronics development and customer support in Europe. And Lars is heading that. Lars used to be the CEO of Gras, and before that worked at Nokia. And we have a strong advisory board. Soren used to be at Bull & Kerr and GN, and Jesper, who used to be the CEO of Sonyon. So to sum, the company was founded in 2019. We have offices in Israel and Denmark, 8 people on board, 10 granted and 5 pending patents, and $2.5 million in seed funding.
Okay.
And to sum, we are providing a game-changing speaker, enabling new form factor for earphones and beyond, based on patented sound generation technology, realizing a solid-state device just like a transistor or LED, and results in a smaller size, low power budget, and really unparalleled sound quality. A revolution in sound akin to LEDs or transistors.
All right. Okay.
Couple of questions, if you don't mind. So we talk about this concept of modulating ultrasound. So what people are hearing is this envelope of an ultrasonic waveform. Is that a way to understand it? Say, as opposed to a beating frequency type of approach.
Yes, that's a good way of looking at it. What you're hearing is really the envelope. Indeed, if you have a beating, there's no interaction between the two beats unless there's some nonlinearity, and you don't hear anything. So it's not a beating, it's an envelope.
Yep, okay. And this membrane that is creating the envelope, essentially, that's also a solid component?
Yes, the whole device is manufactured using what's called the thin film technology. That means we deposit different layers of material, first membrane, second membrane, and third membrane, and just create it using standard MEMS processing technology. All the membranes are essentially MEMS compatible materials.
Okay, so that goes through SMT and things like that. It's not that they're all temperature tolerant.
Everything is temperature tolerant. It's SMD assembled, and very important because at the end of the day, we're just pushing air. The only vibrations we have are hundreds of kilohertz. We really have 0 vibrations, and all the audio frequencies up to 50, 60 kilohertz. So that if you have any sensors on the same platform, like anything from microphones to accelerometers, bone conduction microphones, or gyros, you really have 0 vibrations. So there's no mechanical crosstalk. You don't need to take care of that when you build up the devices.
Okay. And then one of the things you mentioned was it's insensitive to a rear volume. So I'm imagining that because the actual audio generation is at a fixed frequency or a very high frequency, that part of it, you just have a fixed, sealed, essentially, volume on the rear. So it's behaving kind of like a unipolar sound source.
In a way, yes. Monopolar.
Monopolar, yeah.
So as a pump, it needs, of course, some air to take away or push into, but we can withstand the high pressures. It's a very efficient pump with a relatively high back pressure that we can withstand.
Yep.
So the size of the back cavity is really determined by how much back pressure we need, and about 10 times smaller than the standard back cavity.
Yeah, but that also differs fundamentally from a traditional speaker where the back cavity is setting like a resonance frequency of the whole system. That's not part of this design, right? It's
no,
yeah,
it's not part of the design. In a standard speaker, the back cavity is part of the spring of the system, and if it's too small, then of course the resonant frequency is pushed up, and you get a limitation in the movement of the speaker. For us, that is not an issue.
Yep. And what about dynamic range, essentially? Much level.
So the dynamic range of our speaker is really limited by the electronics and not by anything else. So we have the same, at the end of the day, our algorithms are based on a variation of standard electronics and Class D amplifiers, so we can meet the same performance as a Class D amplifier.
Okay. In terms output compared to it's actually the membrane, I guess, or this aperture size, you expect to get equal to or greater output than an equivalent surface area dynamic coil speaker?
We already have better output pressure compared to a standard speaker. Our aim is ambitious. We want to replace the 11 millimeter driver with a 3x3 active area device. So if we look at our results today, we're already better in terms of the amount of sound pressure that we can create per area. But to really be the main challenge in MEMS technology and any kind of solid state is at the end of the day, you pay as a function of size. And that is why we aim for this 3x3 millimeter device. And the goal is to have the same sound performance as an 11 millimeter driver. So it's an ambitious goal, but we're well on the way to do that. We expect engineering samples in Q1 24. And by that time, we should have comparable performance to the 11 millimeter drive.
Is there anything comparable to the method of sound generation that exists already to this modulation of ultrasonics?
No, this is, to the best of our knowledge, and also as feedback from the many people and customers we've been speaking with, this is a totally new approach. People have been looking for pump speakers. It's a holy grail of sound, especially in earphones and headphones. But there has not been a good realization of this technology up till now. But from our perspective, this is a totally new approach to generating sound, and it changes the dynamics of how sound is made.
Mm. And next question would be in relation to how it behaves, or how it interfaces acoustically with, say, an ear canal or a traditional system. Do you expect to get a similar kind of behavior?
So people design earphones or other audio components typically using a lumped element approach, and some you can use also, of course, simulation software. To use our device in these settings is very simple. We're just a current source. So if a standard speaker is a voltage source with some passive components which depict, let's say, the resonances of the system, the electrical, mechanical, or acoustical resonances, our system is just a current source. And then, of course, you can introduce acoustic resonances like the tube feeding into the ear canal, or Helmholtz resonators, or tubes, or other acoustic elements, and then simulate the devices. Using that methodology, we or customers have designed earphones, we've designed speakers for headphones, also free field speakers. So it's really, I wouldn't say easy, but our device is modeled as a current source. We know what is the airflow out of this device. It actually has airflow all the way down to DC. Like I said, it is a pump. It's a constant airflow from DC all the way to tens of kilohertz.
Yeah, so this concept of a current source in an acoustic system, just trying to, because that was mentioned previously, I was just trying to get a concept of what that means. I think you just explained it in the sense that it's just delivering this energy into the system, but it's not directly influenced by it. So, for example, you're going to have a couple of less resonances because it's not dependent on the stiffness of the acoustic fluid. Actually, its output is independent of that.
Exactly. And if you consider just the basic structure, I mean, when you have a voltage source and you have, let's say, resistance in the past, you have a drop in voltage. On the other hand, when you have a current source, it stays the same regardless of resistance, and it reaches, after it goes also through all the resistances, you have exactly the same current flow. Yeah. So that is why we are more agnostic to what's happening in the past until we reach into the ear, and acoustic meshes or other structures have less impact on the performance that we can provide. Of course, if we have things like leakage and other aspects that does have an impact. If you have leakage, then not all the air is flowing into the ear canal, but some is out. But we use leakages, for example, In a standard speaker, we have increasing SPL at 20 dB per decade as we go down in frequency. That's very good for ANC, but in some applications, people want to flatten that out. We can do that using leakage and similar structures. Also, the leakage can have a good interaction for higher order resonances. If you want to, let's say, have a resonance at 3 or 5 kilohertz, we can tailor that using a combination of leakages and some acoustic resonances.
How about distortion or linearity of device? Is that a difficult thing?
No. Our harmonic distortion is really dictated more by the structure. Even though we have an electrostatic actuation, all the non-linearities related to the actuation are appearing at twice the frequency. So we work at 400 kilohertz, everything is happening at 800 kilohertz and doesn't really get to the audio band. So it's a question of optimizing the structure and making sure that we don't introduce unintentional nonlinearities. We see good performance, and really the only dominant harmonic distortion is the second harmonic, which we can also bring down using digital processing.
Mm-hmm. Very good. Excellent.
All right. So maybe on the commercial side, Ari, we could so I saw in the presentation there that targeting earbuds, that's obvious, and also some other kind of wearable things. How are things going in commercialization? I guess when could people possibly see these delivered to products, and when are you ready to take orders to ship for people that see this and they want to get involved? Are we ready to go today, or what timeline are we looking at?
So we actually, if we look at our timeline, right now we have samples which are not final yet. That means we're not meeting the final spec that we target. That would be ready in the first quarter of 24, where we will have engineering samples of the chipset. If you remember, our solution is based on 2 chips. One is the MEMS speaker and the other is the ASIC. Yeah. We will be providing samples at Q1 24 as a design win or pre-design win solution to customers, or maybe a little bit before already providing evaluation boards, which we have right now with our MEMS chip. Mm-hmm. At present, what we're doing is providing selective companies or customers an evaluation board with the MEMS chip we currently have. Okay. So we are selective right now with the customers, but in Q1 24, we'd be more open in providing samples towards a design win.
Okay. And just as you mentioned, the ASIC component and the MEMS component, is there any other special external components people would need for this system, or it's I think Modi might have said it's a drop-in replacement. Is that's how it is?
So the input is actually a digital input. It could be a PDM or an I2S, and it all depends on the interface of our customers and how he would like to interface with our chip. So we're trying to simplify things for the customer by not touching the analog side of things. We are dealing with the whole thing from the digital side up to the generating of the actual sound.
Okay. All right. Very good.
That's interesting. That's interesting. So yeah, it's actually it's pure digital. It's not just digital up to the speaker coil type of thing.
Exactly. I mean, we think since it's non-trivial to deal with the analog side, we think that it would be makes more sense for us to deal with the whole thing. And you know, it's as you probably know, the de-amplifier, there's so many versions and so many companies say that they do it better than anyone else. So we're still, I mean, we'd have a good one and we'd be improving it as we go along, because there's always ways to improve it, as like any other speaker, amplifier of speakers. But it would be done by us.
But it also just makes sense fundamentally, doesn't it? Because what's the point in converting a signal to analog only to convert it back to digital later on?
Yeah, right.
Yeah.
Exactly. So that's why.
Yeah. Historically, you need to work at high bit rates to minimize the latency. So I would say that only in the last 2 years or so, we've started seeing ANC solutions based on digital paths and going from digital microphones to potentially digital speakers.
Yep.
And because it is like this solid state process, the uniformity between the drivers is 100%. So that's
Right.
something.
So that
Yeah.
makes it easy on our customers, especially in the earbuds and other devices that require two speakers that need to be evenly sounded.
We've all seen at the factories people sorting the different drivers into A, B, C, and D baskets.
Right.
So that's
Different bins, yes. Right.
Exactly. Okay. All right, Simon, do you have anything further to ask today?
No, I think that's a bit to get your head around, actually, as a traditional speaker person. So, what is there to ask at this point?
Okay. All right. So we'll put the contact information below and how to reach out to Sonic Edge if you guys are looking for more information. But we thank you, Modi and Ari. Thanks for taking the time to introduce this to our audience today. We appreciate that.
Thanks you
for the opportunity. Yeah.
Okay. All right. So everybody like, subscribe, share, all that good stuff. And we're on Spotify and Apple and YouTube. So please subscribe. Thank you.